In the previous video, we looked at the structure of a segment tree. Here, we're going to review some of its properties. So the main property of a segment tree is that the set of intervals that we store at the node V have the property that can completely span the range of that node V. That's very different from the property that we had for an interval tree. Sometimes people can confuse interval trees and segment trees, so it's important to emphasize the main difference between them. They both store a set of intervals at each node. The main property of the intervals that we store at an interval tree is that they intersect this middle point. So what we know about this intervals that I store in an interval tree is that they include an x-coordinate. They include a single x-coordinate. In other words, if I draw a vertical line, all of them intersect this vertical line. That's very different when you go back and when you look at a segment tree. In the segment tree, they have to span this range, okay, which obviously means that they have to intersect one coordinate, let's say the middle coordinate, but they have to do much more than that. They have to completely span this range. In other words, segment tree to be able to store at a node of a segment tree has the interval has to be much more restrictive. In other words, what that gives us is that it is easier to answer queries in a segment tree compared to an interval tree. We have much more structure. One way to see this is to essentially look at the queries that we want to answer. I want to claim that it is relatively easy to get this query time to find all the line segment intersecting a vertical line segment here. Even if these line segments are not, even if the input line segments are not horizontal, just to show that, let's try an example. So imagine that I have this node V and its range is this slab, and then I have a bunch of input line segments that are disjoint line segment that completely span this X range. So maybe they look something like this. Okay, and I want to given a query line segment like this, I want to find those that intersect this query line segment. Okay. So here it's not too difficult to give a data structure, because what I can do here is just store these line segments in an array. So 1, 2, 3, 4, etc. And then I just need to do a binary search. I look at the middle line segment. If the query is completely above or below this middle line segment, then I can just recurse to the above or below. If it intersects, then I just report this, and then I recurse above and below. And that's basically is the query. That will easily give me log n plus k, because I have either a recursion or I produce an output. So that gives me log n plus k query time. So it only remains to analyze the space of this data structure. The space turns out to be not too difficult because of the properties of this interval of this segment tree. The claim is that every interval is stored at most twice per level. Okay. So let's prove this main claim. But it is obvious that if I prove this claim, then the space is on log n, because if every interval is stored at most twice per level, well, there are log n levels in a segment tree, so therefore the space is on log n. So to prove this, let's do proof by contradiction. Let's assume that an interval is stored 3 times. Let's say over here, and over here. To see how we can get a contradiction, let's say that these intervals have the following ranges, right? So this interval V1 has this X range, V2 has this X range, and V3 has this X range. By the property of the interval tree, or sorry, segment tree, for a segment to be stored in V1, V2, and V3, it must span all of its ranges. Okay, so it has to be something like this. But if you have 3 nodes at the same level, 2 of them, first of all, they have to be consecutive, because this interval defines a consecutive interval in its x range. So if it spans if it spans, let's say, the node the range of v1 and v3, it must also span the range of any interval that is any interval that's between them. Okay, so it spans the interval of consecutive nodes at this level, and if it spans 3 or more, then it must span 2 intervals that are siblings of each other. So therefore, it spans the interval of the parent of them. So therefore, and that follows that therefore I cannot store them in both of them, because if an interval spans the interval of parent, then I store it at the parent. Okay. But an interval is allowed to span 2 nodes. For example, let's look at this picture. For example, if you look at this interval like this, it could span the slab of that node and that node, which is fine because those things are not sibling. But now you can see that if I add any other node to this, if it spans this one, then I have 2 nodes that are the siblings of each other. So therefore we can see that this claim holds, so therefore every interval is stored log n time, so we have n log n space. And that's the major difference between an interval tree and a segment tree. An interval tree has linear space, whereas a segment tree has n log n space. The main property that we buy with the segment tree is that the segments that are the intervals that we store at every node are much nicer to deal with in terms of query time. And building it is also not very difficult. Okay, so putting everything together, we can see that segment tree gives us this structure. And going back to the windowing problem, we have these results that we can get this, and you could, in fact, with some slightly more complicated technique, you can cut down 1 log factors. We have already seen how to kind of cut down this part, although not for arbitrary orientation, but for horizontal line segment. This was the exercise of last week. And you can also do this over here. In general, the technique that allows you to do this cut this log factor is fractional cascading, but we don't have time to talk about that. That's slightly more advanced. But that then concludes this video.